In this section, we'll learn about a data structure called queues. We want to learn about queues because it's used in programs where ordered tasks is important. It's used in places such as the breadth first search and load balancer. And in interviews, you may be asked about how they work, when to use one, and how to implement one. So let's get started and learn about queue. First, let's learn about the definition of queue. Queue is an ordered collection of items where items added first will be removed first. This property is known as FIFO, which is an abbreviation for first in, first out. To bring up real-world examples, cafeteria lines can be represented as queues. The person who lined up first will be the first one to be served. As other examples, printer queue or the customer support queue can also be represented with the queue data structure. Now, let's go over the interface of queue. Queue has two main operations. One of them is called push or enqueue, and this means to add a new item to the rear or tail of the queue. Another main operation is called pop or dequeue. This means removing an item from the front or head of the queue. And queue also has these other operations. One of them is called peek, and this returns the first element in queue without actually moving the element. Another operation is size, which evaluates the size of the queue. And lastly, another operation is called isEmpty, which checks whether the queue is empty or not. Now let's learn about the implementation of queue. Queues can be implemented in two ways. One way is to use a linked list, and another way is to use an array. In this lesson, we'll focus on implementation that is using an array. First, we need to determine whether the queue's front or head is going to be at the beginning of the array or at the end of the array. For this case, we'll assume the queue's front or head is going to be at the end of the array. Now, if we were to see the implementation, here we have a class called queue, and it's initialized with an attribute called items that has an empty array. And we also have a helper operation called isEmpty that will see if this items attribute is empty or not. Next, we'll look at one of the main operations called enqueue. Because we set the queue's front or head is going to be at the end of the array, the reverse is going to be true, which means queue's end or tail is going to be at the beginning of the array. This is why when we do enqueue, we're adding an item to the beginning of the array. This code is written in Python, but this is why we see the item being inserted at the 0th index of this array. Moving on, we also have another main operation called the dequeue. Because queue's front or head is at the end of the array, we can call the pop function, which will remove the item at the end of the array and return this element to you. Lastly, we have another helper method called size, which will return the size of this queue to you. Now, let's review the time complexity of the queue operations. First, for array-based implementation, it's going to matter if the queue's front or head is at the beginning of the array, or if queue's front or head is at the end of the array. In the previous example, we said that queue's front or head is at the end of the array. In this case, the push or the enqueue operation is going to be O of n. This operation is O of n because each time you push or enqueue an item to a queue, you will have to shift each items in the queue over by one spot. On the other hand, the pop or dequeue operation is going to be much faster. This can be done in O1 or constant time. In contrast, the story is going to be different if queue's front or head is at the beginning of the array. In this case, the push or the enqueue operation would take on average of O1. But the worst case is that this operation could still have the runtime of O of n. And this can happen for dynamic array when array resizing takes place. On the other hand, the pop and dequeue operation would in turn cost O of n time. Now let's review the time complexity of the linked list-based implementation. This is going to depend whether we have a stored pointer to the real node or not. If we have a stored pointer to the real node, then the push or enqueue operation is only going to take O1 or constant time. This is because we can know right away where to end this new item to the queue. On the other hand, if we don't have this stored pointer to the real node, then we'll have to scan through the entire linked list and get to the end of the linked list each time. Because of this operation, the runtime of push and enqueue for that case will be O of n. However, linked list-based implementation has a constant time operation for the pop or date queue operation.